So we're going to begin lecture 12. We'll look at three new categories of instructions: rotate, bit test, and bit scan. The homework 3 is due Thursday, June the 5th. First, let's see what's the difference between the new instruction we're going to talk about rotate and the ones we already discussed last week, the shift instructions. Shift instructions discard bits that are shifted out. However, rotate instructions take bits that are shifted out and use them to fill the empty locations or empty bits on the other side. That's their difference. Rotating instructions, they use similar format to the shift instructions. Opcode destination, comma, shift amount, or in this case, rotate amount. Destination may be register or memory. And the amount of shifting or the rotation can be an immediate number or a register CL. All rotating instructions store last bits shift out of in carry bit. We have four kinds of rotation instructions: ROR, ROL, RCR, RCL. The first R, letter R, is the rotation, and the last letter, either R or L, indicates the direction of the rotation. So ROR is rotate to the right. The operation of this ROR instruction is that we're going to shift the bits from destination operand to the right by that many bits, and the least significant bits will be moved into most significant bits. So it's like a circle, loop. So the bits shift out of from one side will be copied back in to the other side. ROR is similar. The direction is to the left. The next two rotation instructions, RCR and RCL, are rotation through carry bit. You'll see when we illustrate these two instructions, their operations are different from ROR and ROL in that the last bit or last bits coming out of the register or memory will be put or copied into the carry flag, and the carry flag will be used as the new bits fill out on the other end of the operand. So basically these two instructions, RCR and RCL, treat CF as an extra least significant bit. Let's start with this ROL example, rotate to the left. And we use this ROL AX, 1. So the destination operand is AX. The amount of shift is 1. Let's assume that before the execution of this instruction, we have 1, 2, 3, 4 in AX. And we can easily represent the number in binary. The count is 1, and also let's assume carry flag is 0. In this diagram, on the top, this is the value, the bit values in AX before the rotation instruction. So we have this 1, 2, 3, 4 hexadecimal number representing binary here, and carry flag is a 0. The value of all bits of AX are rotate to the left for 1 bit. So as you can see, all the bits are shifted to the left for 1 bit. So bit 0 is now moved into bit 1, and bit 1 is now moved into bit 2, and bit 14 is now moved into bit 15. The most significant bit, bit 15, is not discarded. That's the difference between rotation and shift instruction. This most significant bit is copied to the least significant bit side. So that's going to be copied to bit 0. At the same time, this bit is copied to carry flag. So after the execution of this instruction, AX now has 2468. Again, you can see that this is exactly twice of the original value. And the bit copied to carry flag is 0, so the carry flag after the execution is 0. Our OR is rotation to the right. In this example, we have ROR AX, comma CL. And let's assume that before the execution of this instruction, we again have 1, 2, 3, 4 hexadecimal in register AX. CL has 4, and the carry flag has 0. The value in all bits of AX are rotate right for 4 bit positions. So starting from this bit 15, you can see this bit is now shifted to the right for 4 bits. So now it's going to be bit 11. Bit 14 is now bit 10. And this bit 4, originally bit 4, is now at bit 0. The first bit, the bit 0, shipped out of the register. This bit is now bit 12. Okay, and then bit 1 is now 13, and bit 2 is now bit 14, and bit 3 is the new bit 15. And bit 3 is the last bit shipped out of the register, and that's the last value copied into carry flag. So the carry flag now has the value, I believe, the 0. So the operation of this instruction is that the value of all bits of AX are rotated to the right for 4 bit positions. Values rotated out of the least significant bit are reloaded at the most significant bit side. Values rotated out of MSB copied to carry flag. So if you try to figure out the final value, essentially you can think about this as rotation by 1 bit but for 4 times. So the last bit rotated out of the register will be the bit 3. So that will be the last value copied into the carry flag. The previous 3 values will be overwritten by the most recent copy. So after the execution, we have this 4, 1, 2, 3 in AX, and we have carry flag at 0. Yeah. What is it? This one?
Yeah, no, the second one. Yeah.
Oh, yeah. Yeah, this is 2 is the subscript. I don't know what's happening here with the projector. Okay, this next instruction, RCL, note this letter C in between this R and L. R stands for rotation, L stands for left, and this C stands for through the carry flag. So what we're doing here is we're still doing the rotation, but when we rotate, we're going to use the carry bit. We'll use the value on the carry flag as the ones that are going to be filling into the empty bits. So that's the meaning of this through. So this carry flag is now used as another most significant bit. So the value in the carry flag will be reloaded to the least significant bit side. And this is the direction is to the left. And we can also have rotation to the right through the carry bit. So in that case, the the least significant bit will be loaded into the carrier flag, and the carrier flag will be loaded into the most significant bit side. But let's get back to this example. We have RCL BX, comma CL. Before the execution of this instruction, let's assume that we have this 1, 2, 3, 4 hexadecimal in BX, and we're going to rotate for 4 bits, and initial carrier flag is 0. So we'll have all the bits of AX shifted to the left for 4-bit positions. The emptied MSB are rotated through the carrier bit back into the LSB, as we show it in this diagram. This means that bit should be 15 because BX is a 16-bit number. This most significant bit is going to be copied into carrier flag, and the initial value of the carrier flag will be loaded to the least significant bit side. The last value rotated out of MSB is going to retain in the carrier flag. And first rotate loads prior value of the carrier flag at the least significant bit. So if you do this rotation, because we're doing 4 times, so this 0010 is going to be now on the most significant 4-bit. All this 0001 are shipped out of the register BX. But they're not lost, they are actually copied back to the other side. The last bit shipped out of the register is 1, and this 1 is going to be copied to the carrier flag. So the carrier flag at the end will have 1, and this 1 comes from this 1 here. I said what? Yes, 1 is eventually in the carrier flag because 1, this bit is the last bit shifted out of the register, and that last bit is copied to the carrier flag.
And then is that one shouldn't the one be part of the value according to the diagram?
So the last bit,
It's copied to bit 0.
the last bit, the bit 0 of this register will have the value of the carrier flag. So
Which is 1. Or is the previous value?
the previous.
Okay.
Yeah. So all the bits are kind of in a queue, and you push them one by one. Is it clear? Yeah, exactly. So you treat this carrier flag as another most significant bit. Okay, let's look at some examples. We assume that in AL register we have 4, 3 in hexadecimal, CL has 4, and initial value of carrier flag is 0. Show the state of AL after each instruction in the sequence below. So I'll give you 2 minutes to work on these 4 instructions, and these 4 instructions are executed one after another in sequence. So the later instructions depending on the value of earlier instructions. All right, let's look at the solution. So initially, AL has for 3 in hexadecimal. You can write down the value in binary. That's going to be 0, 1, 0, 0, 0, 0, 1, 1. First instructions ROR AL, 2. So we'll look at this binary value. We're going to do rotation to the right. And it's not through carry bit, so it's simply copying the last bit to carry flag. So this last 2 bits going to be shifted out of the register, and then they're going to be copied, well, loaded again to the most significant bit. So this 1, 1 come back here. Now if you want to really be clear, this one, very first bit shift out of the register will be this one, and the second one is going to be this one. And because this one is the last bit shifted out of the register, and this is the value copied into the carry flag. So after this instruction is completed, carry flag is 1. Next instructions are OL, AL, CL. So we're going to use the most updated value in AL, which is 1101, 0000. CL has 4, so we're going to rotate to the left for 4 binary bits. So all these 4 bits will be shifted out of the register AL, and they will be loaded to the least significant bit side. And this is the first bit coming out, so this is the 1. The second bit coming out, that's the second. And then the third bit coming out, and that's the third bit. And the fourth bit coming out, that's the last bit coming out. And since 1 is the last bit shipped out of the register, so this 1 is copied to carry flag. So carry flag again has a 1. So now we have this value 0000 1101 in register AL, and we have CF, the carry flag is a 1, which is the one I write down here. And we are going to rotate to the right through the carry bit. So we're going to use the carry bit, which is this one, as an additional least significant bit, because we're doing to the right. So we're going to put CF on the right side. If we're doing rotation to the left, this carry bit will be putting on the left side, just for easier to understand. So this is the bit sequence, including the carry flag. And we're going to rotate to the right by 3 bits. So this 0, 1, 1 will be shipped out of the register and carry flag, and then loaded again to the other side. So this is the first bit coming out, and this is the first bit, second bit, and second bit, and third bit, that's the third bit. Okay, and this additional bit, this is the one going to be loaded into this carry flag. So after this rotation, AL has 0110 0001, and then also carry flag has this 1, because that's the one coming out of the out of the register. The last instruction, rotation, yes. So this third instruction depends on the second instruction, which causes the carry flag to be a 1. So the first instruction, we assume the carry flag is a 0. So that's why we use 0 on the carry flag for the rotation. And these 4 instructions are executed one after another in sequence. So they are part of a program. And their immediate or their result will affect the following instructions. So not only their values in AL, AX registers, but also the carry flag will affect the following instructions. So that's why this 1 comes from the second instruction, because the second instruction caused carry flag to have a 1. The last instruction, RCL AL, 4, because we're rotating through the carry flag to the left. This L, that's to the left. So this is the value in AL, and we put the carry flag on the most significant bit side. This is the carry flag. And we draw this line to indicate that these are the 4 bits will be loaded to the least significant bit side of AL. And this 0 is the one eventually moved out of the register AL. So this will be put into CF, the carry flag. So after this instruction is completed, AL has this value 0001, 1011, and carry flag has a 0. This clear? Okay, let's move on to a new categories of instructions. They are called bit test instructions. And we are talking about 4 different kinds of bit test instructions here. The very first one is the plain bit test. And then we have bit test and reset, bit test and set, and bit test and complement. Bit test, by the name you know that we're going to test the value on a particular bit from a register or from an operand. And we may do additional operations on that bit. That's what these 3 instructions are for. The format of these instructions are the same. So the upper code, or mnemonic, BT stands for bit test, or BTR, BTS, BTC. It takes 2 operands, destination operand and source operand. Destination operand holds the value to be tested, and the source operand is an index that selects the position of the bit to be tested. Okay, so this is the index. And take an example of register AL, which is an 8-bit register. So the index range will be from 0 to 7. If you have the destination operand as AX, well, AX as a destination operand, and that tells you 16 bits, so the index range will be from 0 to 15. We always count from 0 for the index. The operation of this instruction enables programmers to test bit in a value in register or memory. All these instructions will save the value of the selected bit in the carry flag. This is actually during the testing. Okay. When we test the bit values, the values of a bit, how do we know, or how do we store the result of the testing? We in fact use this carry flag. Because the value of the selected bit will be saved into carry flag, so for the next instruction, typically a conditional branch instruction or conditional instruction of some kind, they will use the value on the carry flag, which is set by this instruction. So that's how we use the bit test instructions. Bit test, this plain bit test will leave the selected bit unchanged, whereas BTR will clear the bit. R means reset, will clear. BTS will set the bit, and BTC will invert the bit, will complement the bit. Let's look at a few examples. First example is BTC BX, 7. Bit test and complement. So we're going to test a bit of BX, and we're going to complement the bit after the test. And which bit? The 7 gives you the index. So out of the 16 bits of BX, we're going to test bit 7. Let's assume that before the execution of this instruction, we have 03F0 hexadecimal in BX. We can then represent the value in binary. So it's going to be 000, 0011, then 1111, and then 0000. Starting from this bit 0, when we count bit 7, that's actually this bit, which is highlighted in red. So this is the bit this instruction will test. Now, what does this instruction do exactly? It will save this value, the value of this bit, to carry flag. Because this value here is 1. That's what we gave to BX. This 1 will be saved into the carry flag. So the carry flag will be a 1 after this instruction is completed. Also, another operation this instruction will do is the complement. It will change the value, that bit 7. It will invert it. Since the original value is 1, after the complement, after invert, we will have 0 on bit 7. So after this instruction is completed, you have 0370 in BX. And also this carry flag has a 1 because of the test. This clear? I don't have examples of the other 3 instructions, but they are very much similar. If you have, let's say, if you have a BTR, R stands for reset or clear. Then for this instruction, what will be the value on CF after its completion? So we're looking at here, if I change the C to a R, so BTR, that's bit test and reset. So the CF will still the same 1 because it's going to save this value. The original value is 1, so it's going to be a 1 again. Yeah. So if it is R, so we're going to reset that bit. Again, the final value on this bit 7 is at 0, the same as BTC. Can you say that again, please? Yes, that's just we just discussed. If we have a BTR for the bit test, this 1 will be saved to carry flag. Okay, if you want here to be a 0? Okay, let's just say we have a 0 here for the original value, and are we gonna looking at BTC or BTR? So BTR instruction. So the carry flag will be a 0 because the original value is a 0. Because R, so that's reset. So 0 still it's a 0. Yeah. Make it 1, yes, if it is set. If it is clear or reset, that's to make it 0. Okay, the next categories of instruction we want to look at is so-called bit scan instructions. It actually has 2 different instructions for different directions. BSF and BSR, forward and reverse. The format of, well, both of these 2 instructions are going to scan the operand to find out the first non-zero bit. format of these bit scan instructions: BSF or BSR destination source. The source will hold a value for which bits are to test it. So that means the source is not the one you're going to change, and instead the source is the one you're going to be scanning to find the first non-zero bit. Destination operand is the index of the first bit that tests as non-zero. These two instructions allow the programmer to test value to determine if all bits are zero. For BSF, scans bit starting from bit 0 and set the 0 flag is 0 if all bits are found to be a 0, and set ZF to be a 1 when the first bit detected, and place the index of that bit into destination. And BSR is doing the opposite direction. So both of these two instructions are going to do two things. One is to set the 0 flag, and depending on this source operand is a 0 or not. If it is a 0, this carry flag will be set 0. If it's not 0, the 0 flag will be 1, and the first non-zero bit, the index of that bit, will be put into the destination operand. So let's look at this example: BSF ESI, EDX. So we're going to scan EDX because EDX is the source, and the index will be put into ESI. We know EDX is a 32-bit value, so we'll scan it, and we have three scenarios. If EDX has a 0, then the scanning will find out that, oh, there's no non-zero bit. So it is a 0, so we're going to put 0 on the 0 flag. The second scenario is when we have a 1 on EDX, and it happens to be the least significant bit of EDX. So when we do the scanning, because this is BSF, that's scan forward. By forward, we mean we're going to scan from the least significant bit. So we're going to scan from bit 0 to all the way to bit 32, because totally we have 32 binary bits. And when we start scanning, we immediately find that this bit 0 has a 1. So that's a non-zero bit. So we'll put this non-zero, or put the index of that bit, that is to put the 0 into ESI. Let me say it again. We found a 1, that's a non-zero bit, and that's the first non-zero bit we find if we scan from right to left. Okay? So the index of that non-zero bit is 0, and that index will be put into ESI, which is the destination operand of BSF. Also, this instruction will set 0 flag as a 1. The next scenario where we have 00003000. This is hexadecimal, by the way. If you write down in binary, you can see this 3 is 0011, and that's bit 12 and bit 13. Because we have, starting from here, we have bit 0 to 4 and 5 to 8, and then 8 to 11. And this 3 is, we have 1 1 for 3, and that's bit 12 and bit 13. And we're gonna scan again the same direction from right to left. So bit 12 is the first non-zero bit we will find. So the index for that bit is 12. And that's why you see a C, which is 12, put into ESI, that's the destination operand. That's to say, on bit 12, we have a non-zero bit, and that's the first non-zero bit we found. ESI is a register. C just is just a value in hexadecimal. So there's because ESI should have a value 12. That's the index of that 90 bit, and C is 12. So this is a number. This has nothing to do with bit anymore. It's just a number, a value, 12, stored in ESI. Clear or kind of clear? Okay, now we have 5 instructions, and let's say we have these values on the board, and DS as 2, 1, 1, 0. So assume we have 2110 in DS data segment register, and also on the board I give you the initial values of certain memory locations. The way I represent these values is that I parentheses indicate at that physical location, at that email address, we have a word, and the value of the word, for example, in this case, at address 21102, both algebra in hexadecimal, we have a word that is 1010. So let's work on these 5 instructions. And you can assume these 5 instructions are independent, because even though they can be in the same program, they actually don't have any effect to one another. So you can assume these 5 instructions are independent. That's the index. That's which bit. Yeah, that's bit 4. Tested. And again, we count from the least significant side, and we count from 0. Just to give you a hint, for the first one, you will need to first find out what is the memory address, right? It's going to be DS:02. And then you do the shifting and you plus 2, so you will actually get this address. And we already tell you that at this address, we have a word 1010, so that's the word you will do the test. Okay, let's look at a solution. First instruction, bit test word pointer bracket 02, comma 4. So first thing we need to look into is the address of that memory operand. So that's DS:02. After doing the address translation, we know the linear address is 21102, because we did shifting and we did addition. And the word at this address is 1010 in hexadecimal, and if you can represent the same value in binary, you can figure out on bit 4, that's this bit, that's actually a 1. So you will save the 1 into carry flag.
So they sort of complete this. We'll just do it separately. We just drop them directly into the carry flag.
That's right. So bit test will just copy that bit into carry flag. That's how it does the test, because it's the next instruction will use that test result, which is stored in the carry flags. Second instruction is BTC, so bit test and complement. Again, we're going to first calculate the linear address, so that's going to be 21110, and the word at that location is 001E. This is the binary representation, and we're going to test bit 1, so that's this one, this bit. We're going to save the value of that bit into carry flag, and we'll complement that bit. So this bit will have a 0 after the instruction is completed. That means the memory content at that address will be updated. Next instruction, BTS, that's bit test and set. We're going to look at this address, 21104, and this value is given, 0189 is the original value at that location, and this here is the binary representation of that value, and we're going to take bit 1, and we're going to save the value, it's 0, to carry flag, and because this BTS is set, so we're going to change this 0 to a 1. So that's this 1 here. At the end, this instruction will change this word to 018B. Next instruction, BSF, so bit scan forward. We have this location 0E, the effective address is 0E. We first calculate the linear address, the 2110E, and we know that at this location we have 00FF, that's the original value, and if we write the value in binary, so here's the binary representation, what we'll do, scan, we're going to scan forward, that means we're going to start from the least significant bit going to the left, and because we found a non-zero bit, so that means this word is not a 0, so we set carry flag as a 1, and the first non-zero bit is just this very first bit, so that's bit 0. Again, the index is 0. So we'll put this 0 into the destination operand, which is CX. So CX will have 0 at the completion of this instruction. So this BSF is bit scan forward. So we're going to look at this value. We're going to scan from bit 0 all the way to up to the bit 15. Because we found a non-zero bit, so this whole thing, this whole value is not a 0. So we set the 0 flag to be a 1. Also, we happen to find that the very first bit, bit 0, is a non-zero bit. That index, this 0 is the index, is going to be put into CX, which is the destination operand. So that's why at the end, after this instruction is completed, we have 0 in CX. Yeah, because the very first bit is not 0, and we're scanning from this side, so we just stop there. We found this non-zero bit, we don't want to do the scanning anymore. BSR is scanning in the opposite direction. We're going to scan from the most significant bit to the least significant bit. And for this particular word, it is 0, so we scan all the way through. We found that all the bits are 0. There's no non-zero bit, so we're going to put 0 on the 0 flag, and DX going to be unchanged because there's no non-zero bit. Yeah, so let's say if we have a 1 right here, okay, and this is the, I believe this is bit 11, okay. If we have a 1 on bit 11, then this 0 flag will be a 1 because we found a non-zero bit, and DX will have 11 because that's the index of the first non-zero bit we found by scanning from left to right. Yeah, DX will be 11. Yeah.
When we first learned about the zero flag, I was, the way I understood it, if the zero flag was a one, that means that it was a zero.
Yeah, this is how the
How it works.
yeah, for this instruction. Are you talking about this instruction? Okay. Um, uh-huh. Okay. Okay. So first, this is a bit scan forward. Okay. So we're gonna scan some value forward. That means from right to left, and we try to find the first non-zero bit. So if you are given this value, you have all the zeros and ones in here, and you are scanning from right to left. Which bit is where you find the first non-zero? That's this very first bit. The index of this bit is 0. Okay? Remember, the index of this first non-zero bit is 0. And that index is the value we should put into CX, which is the destination operand.
Why is the difference just going forward and just going reverse if the result is the same?
It's not always the same. For different values, you may find oftentimes different um, index. For example, if you do on the same value, if you do bit scan reverse, that means you're gonna scan from left to the right. In that case, the first non-zero bit you will find is this bit 7. So if you have BSR, then the 7 will be put into CX because that's the index of the first non-zero bit.
Is it not supposed to be forward, left to right, and reverse?
You're gonna pick one direction. So by definition, forward means from right to left, or from the least significant bit to the most significant bit. That's the forward. Like you do it ascending order. So you start from bit 0 and 1, 2, all the way up. Okay, I guess it's a good time to have a break. We'll reconvene in 20 minutes.